Okay, I want to do two more examples of countable sets. The first is I want to show that the set of even positive integers, I want to show that the set of even positive integers has the same cardinality as the integers. And this isn't too much of a step from the previous example where we saw that the set of non-negative integers had the same cardinality as the integers. The even positive integers, I'll just call E again, E for even this time. So that's 2, 4, 6, 8, and so on. The integers themselves, Z, are -3, -2, -1, 0, 1, 2, 3. And again, it's not too hard to see that you can put these in one-to-one correspondence. You can let 2 go to 0, and 4 goes to 1, 6 goes to -1, 8 goes to 2, 10 goes to -2, and so on. Okay, so again, you can figure out, I don't care about what the formula is, but you can figure out exactly what that bijection is if you really care. I do not care, okay? Nor do you have to, okay? I'm not gonna ever ask you to figure out what that bijection is, but just the fact that you can put these two sets in a one-to-one correspondence means that they have the same cardinality. And our final example, which is a little bit more surprising, is that it turns out that the rational numbers, so the rational numbers, Q, so remember that these are the sets of fractions A over B, where A and B are integers, and B is, of course, non-zero. These have the same cardinality as the non-negative integers. Okay. So I want to prove that there's a one-to-one correspondence between these fractions and the non-negative integers. And so what I'm going to do is I'm going to make an infinite array. And here's how I want to do this. I'm going to start with 0. So I'm going to have 0. And what I'm going to do is I'm going to put along, you can kind of think of this like a 2x2 grid. But this is going to be 0 over 1, 0 over 2, 0 over 3, and so on. And we're going to have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And 2 over 1, 2 over 2, 2 over 3, and so on. I'm going to do this slightly differently than I do in the book. 3 over 1, 3 over 2, 3 over 3. Okay. And then we'll continue that infinitely far in that direction. Below that, we'll have the negative values. So -1 over 1, -1/2, -1/3, -1/4, and so on. Okay, and -2 over 1, -2 over 2, -2/3, -2/4, and so on. Okay, so here I have this kind of infinite grid of all the integers that we could possibly have. And if you think about any integer that you want, say 3 over 104, just to pick something random, if you want to talk about 3 over 104, you know that that's going to be somewhere in this list because it's going to be in this row that has all the 3's in it, and it's going to be 104 terms over. It's going to be way off the sheet over there. Okay, so it's going to be in this row, but way off the sheet over there. So every rational number that you can think of, positive or negative, will be there. If it's positive, it's going to be above the row of zeros. If it's negative, it'll be below the row of zeros. And again, what we want to do is we want to come up with a one-to-one correspondence between the non-negative integers and these sets of integers. And so the first thing that we can do actually is notice that we have slightly too many terms here. We're repeating some terms. So we already have all the zeros. So really, we don't need to worry about any of those zeros there. Likewise, if I were to have 2 halves, well, that's the same as 1. And 2/4 is the same as 1/2, and so on. 3 halves is the same as 1. And so we can cross off all the terms that we already have. And likewise, let's see, -2/2 and -2/4 are repeated. And then what I want to do is I'm going to count in the following way. This is a slightly strange order here. But what I'm going to do is I'm going to count in the following way. I'm going to start at 0. I'm going to go up, and then to the right, and then down. I'm going to skip over the terms that we've already counted, and then to the left, and then down, and then to the right, up, 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 to the left, up, to the right, down, skipping over all the terms that we've already counted, down, down, and then go to the left, again, skipping all the terms that we've already counted. And if we count this way, we'll eventually fill up the entire grid. There won't be any number on the grid that we've missed. Okay, and what that means is that we've put them in one-to-one correspondence. Good luck figuring out what this actual function is. I don't care though. All I care about is that we can put them in one-to-one correspondence, and I think that we've demonstrated that. Pretty well. I have a different write-up in the book if you want to look at this in a slightly different way in the book. So I have, first I start with the positive integers, and if you do the positive integers, then you can ignore, so let's just ignore the bottom half. And if you do the positive integers, you can count kind of diagonally like that. And then you can certainly get every value that you want that way. Again, skipping over the values that you've already counted. And then once you have the positive integers, you can just alternate that with the negative ones. And that's essentially what this argument is putting those two together. So again, I have a slightly different write-up in the book if you want to go over that again.